All right, so this sort of mini lecture is about principal stress. So last time, if you remember, we talked about Moore's circle and how we can represent any two-dimensional state of stress. So that's a sigma xx, a sigma yy, and a tau xy. We can actually represent that as a circle, and any sort of location on that circle is a state of stress for a different orientation than the original one. So it was originally oriented in XY space, right? And as we move around the circle, effectively what we're doing is we're taking that stress cube and we're rotating it, right? And as and we'll go through this in some examples, but the rotation on the circle, clockwise rotation on the circle, would be a clockwise rotation of the stress cube, assuming that you're plotting the positive shear stress downward. But the rotation on the circle is twice what it would be on the stress cube. So if I rotate on the circle 180 degrees, right, that corresponds to a 90-degree rotation on the stress cube. Okay, so what I want to talk about today is first and foremost this idea of principal stress, right? So principal stresses are defined in the following way. So for any state of stress, so again, here we're talking about a two-dimensional state of stress. For any two-dimensional state of stress, there exist two mutually perpendicular planes that are free from shear stress. So if I give you a state of stress, and there is no shear, right, that is a principal, those are principal stresses by definition. Because the normal stresses on those planes are known as the principal stresses. So if there's no shear stress, right, then those are principal stresses, okay? And maybe what we'll do, well, let me go through a few definitions. So sigma 1 comma 2, right, these are known as principal stresses. That is the sort of nomenclature, where sigma 1 is the maximum principal stress. And sigma 2 is the minimum principal stress. All right. And then theta p, right, is the angle between the xy coordinate system and the principal coordinates. And so those principal coordinates here, right, so these are the coordinates associated with the principal stresses. What's going on here? There we go. Okay, so I'm going to show this on a Moore's circle in the following slide. But these guys here are some things that we're going to be talking a lot about, right? So sigma 1, 2 are just going to be referred to as principal stresses. Sigma 1 is always the maximum. Sigma 2 is always the minimum. It does not have to be 0 or negative. It could still be positive. It's just the minimum of the two. And then theta p is the angle between the current xy coordinate, so wherever the xy coordinate was given for the particular problem, right? And then the coordinates associated with the principal stresses. So if I start an XY coordinate and let's say I have to rotate it 12.5 degrees in order for these stresses to become, the normal stresses to become principal stresses, right? And the definition there is that the shear stress vanishes, right? So in a state of principal stress, I have no shear stress, right? So that's what we mean by that part, right? They are free from shear stress, right? So that's how we're going to define principal stresses, right? Okay, so let's take a look at kind of what this looks like on a Mohr circle. So I guess I'll start here and here. Right, so this is my sigma. This is my tau. Notice I'm plotting tau positive downward, right? And I can come in here. I guess I'll do it in red, right? And let me draw my little stress cube here. Right. So let's say this guy. Let me do it like this. I'm always going to draw this with the positive sign convention. All right. And then I will use the sign. So here if I say that sigma y equals minus 20 ksi, right? That means that it's in compression, right? And sigma xx, let's say this equals, 40 ksi, like that, right? And tau xy, let's see, 20 squared is that, so I'm trying to think of a round number off the top of my head, but I can't. So let's just deal with this as 10 ksi. Right, and that is tau xy, right? So that's our current state of stress, right? So if I'm going to plot this, right, I can come here and I'm going to plot first sigma xx and tau xy, right? So I come 10, 20, 30, 40, and then I go down 10. So this right here is a positive 40 and a positive 10. Again, like the 10,000th time, we're plotting tau positive downward. Right? And then we look at sigma yy, and we're going to plot sigma yy comma minus tau xy. So this guy here is sigma xx tau xy. And then we're going to come over here, and we're going to plot this guy, which is going to be minus 20 minus 10, right? And that is sigma yy comma minus tau xy, right? And if you're wondering why it's a minus, I invite you to go back to the previous lecture. We spent a bunch of time on it, but it has to do with the fact that when we rotate the coordinates, the shear stress that's on the y face flips from negative to positive. Right? So here I can then draw a straight line. Ooh. Okay, well, let me do that again. Draw a straight line here, right? And that's going to cross right here, which in this case ends up being 10 comma 0, right? Now, why is it 10 comma 0? That's my sigma average, right? So it crosses the sigma axis at the average of the normal stresses, and since it's crossing the sigma axis, there can't be any shear stress, right? So if you notice, these guys are always plotting a positive and then the negative of that shear stress, right? So one point is always going to be a certain dimension below the sigma axis, and the other one is going to be that exact same dimension, but it will be above the sigma axis. All right. Okay, so then we can now draw the Mohr circle, and I'm going to try to do my best here. I don't know how it's going to come out. I think I can do a little bit better than that. Ooh, that time it didn't work at all. So let me try this. All right, that's close, right? So that's our Mohr circle, right? And a couple points that we want to identify, right? So these points here, this guy here, this guy here, and this guy here, they are sigma 1 and sigma 2, right? Those are my principal stresses. So they are the maximum normal stress that I see and the minimum normal stress that I see. No matter how I orient this cube for this particular state of stress, every state of stress has their own unique Mohr circle, right? For this particular state of stress, those are the maximum and minimum normal stresses that I can see. And so if I want to highlight this guy, this horizontal line here, that is associated with the principal stress, right? So always the horizontal line along the sigma axis is always associated with the principal stress, because there is no shear stress there, and that is the definition of principal stress. Okay, so then I can come in here, maybe I'll keep it blue, and I can define this angle here, right? That angle there is 2 times theta p. Let me do that a little bit clearer. 2 times theta p, right? Now, why is it twice? Because when we defined the Mohr circle, we identified that a theta rotation on the circle is equal to a 1/2 theta rotation on the stress cube, right? Or a theta rotation on the stress cube is equal to a 2 theta rotation on the Mohr circle, right? Okay, and the other thing that I want to point out here is that this point here, right, and this point here are my tau min and tau max. Right? Now notice, the tau min and the tau max are always the exact same magnitude. Right? Because the circle is always centered on the sigma axis, that means that tau min and tau max are the same. Right? And every state of stress has a balanced min and max tau. And you can notice that they are always 90 degrees from the principal axes, right? So the principal axes define the minimum shear stress, which would be 0, right? That's sort of the axiom that we started with, right? And 90 degrees on the circle, or 45 degrees on the stress cube, that's where we can get to the tau min and the tau max. Right? Okay, so then the last thing we've got to do here is to calculate the radius of the circle, right? And we can do that. This guy here, for this particular situation, right, is 30 ksi, right? And this guy here, right, is 10 ksi. Okay. So what is the radius? Well, the radius is going to equal 30 squared plus 10 squared square root, right? So what is that? That is 900 plus 100 square root, so square root of 1,000. Not exactly sure what that is, but it's probably something on the order. In fact, let me just do this quickly. Where is my, I'll just use Excel. Here we go. So we'll do 900. 900 plus 100. And then I'm going to take the square root of that. And so that is 31.6 KSI. Right? So that is my radius. Right? Okay, so now what is sigma 1? Right? Well, sigma 1 is going to be sigma average plus the radius. Right? So this will be sigma average plus r, which in this case would be 41.6 KSI. Okay, sigma 2 is always going to be sigma average minus r. Right? So I could do that, and this is going to be minus 21.6 KSI. Okay. Tau max is always going to equal r, right? You can see it's exactly a radius. So this is 31.6 KSI. So if I give you a state of stress like the one I've done in the upper left, and I say, please calculate the principal stresses and maximum shear stress, you just locate the center, draw the circle, right? Then this guy here, right, and maybe I'll highlight it in pink here, this guy here is just representing a triangle, right? And the horizontal base is 30 KSI, the vertical component is 10 KSI, and the hypotenuse is R, right? Excuse me. And so that's how I can always remember what that expression is. You can go back to the other expression, right? And it is, it'll work out to be exactly the same. It's just a lot harder to remember than the horizontal component squared plus the vertical component squared square root, right? And so then we just have to calculate this guy here, which is theta p, right? And here, in fact, you know what I'll do, because I didn't work this out and I don't really have any more space here, we are going to do this in the next examples, not in this one, but effectively what it is the inverse tangent. So it'll be 2 theta p equals the inverse tangent of opposite over adjacent, which in this case would be 10 over 30, like that. Right? And that would, that inverse tangent of 10 over 30 is theta, right? Is the total angle there, but we're defining that total angle as twice theta p being defined as the angle on that stress cube. All right, so that's it for principal stresses. I think the big takeaways here are a principal stress is a stress on a face when there is no shear stress. Right? Any state of stress that I give you will always have 2 perpendicular directions that are free from shear stress. And you see that right here, right? Because that circle is centered on the sigma axis, it crosses the sigma axis in 2 places. Those 2 places are 180 degrees apart on the circle, which means they're 90 degrees apart or mutually perpendicular on the stress cube, right? And they're free from shear stress because they're located on the sigma axis, right? So those are sort of the